Welcome to the another module of this course, Computer Aided Power System Analysis. We have been discussing the Newton-Raphson load flow in the polar coordinate. So far we have discussed that after the linearization, the basic equation corresponding to the Newton-Raphson load flow in polar coordinate is given by J, matrix J into delta x vector is equal to delta m vector, where this matrix J is nothing but the Jacobian matrix, and this matrix J is given by J1, J2, J3, J4, where J1, J2, J3, J4 are the Jacobian submatrices, and we have also defined their dimensions, we have also defined what they stand for, and we have also looked at the analytical expressions of the elements of the matrix J1. So, now we have to look at the analytical expressions of the elements of this matrices J2, J3 and J4. So, to do that, let us again recollect our basic expression of the power flow equations. So, it is given by Pi is equal to K is equal to 1 to N Vi Vk Yik cos theta I minus theta k minus alpha ik. We have already defined what these quantities are. Qi is equal to K is equal to 1 to N Vi Vk Yik sin theta I minus theta k minus alpha ik. Here we again recollect that Pi and Qi are nothing but the injected real and reactive power at bus I, and this Pi is for I is equal to, this is I is equal to 2 to N, and this Qi is for I is equal to m plus 1 to N, and we have also defined what is N, what is M. N is nothing but the number of buses, M is nothing but the number of generators, and our convention is that bus 1 is the slack bus, and then buses 2 to M are the generator buses, and buses m plus 1, m plus 2 up to N, and the are the PQ buses. Now, J2 we have also seen that J2 is given by, J2 matrix is given by del P by del V, where P is a vector, V is a vector, where vector P is given by P2, P3, Pn transpose. So, this is an n minus 1 cross 1 vector. Vector V is given by Vm plus 1, Vm plus 2 dot 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 Vn transpose. So, this is an n minus m cross 1 vector. So, then therefore, del P by del V vector would be, and we have also seen that del P, the expressions of this, the matrices are del P2 by del V plus 1, del P2 by del V plus 2 dot 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 del P2 by del Vn, and then it goes up to then del Pn by del Vm plus 1, then del Pn by del B2, and then last is N. and it would be essentially an n minus 1 cross n minus m matrix. So, then it is a rectangular matrix. So, then therefore, there is nothing called a diagonal element, and also there is nothing called an off diagonal element, but then there would be some terms where the index of p and the index of v would be same, and there would be other terms where this index of p and the index of v would be different. So, the terms will have in general in this nature del pi by del vi. You please note that this index of p, that is I, and this index of v, that is I. So, they are same, and then also there would be some term which is del pi by, let us say, del vk, where k is not equal to I. So, this we call, let us say, a self term. Example, and we say, let us say, we should not say mutual term, let us say non self term, it is just a matter of terminology, non self term. The examples of this non self terms would be something like this, say del p 2 by, let us say, del v, let us say 10. For example, if say n is equal to say 100 and let us say m is equal to say 8. So, then del p 2 by del v 10, del p 59 by del v 98. So, these are the examples, some of the examples are these are the examples, and here these examples are, for example, del p say 58 by del v 58, say del p 99 by del v 99, etc. So, these are the self term where this index of p and the index of v are same. Here this is 58, this is 58, here this is 99, this is 99, but here this index of p and index of v are different. So, we have to, so then we have to actually derive the analytical expressions of these two general terms. So, now for that we again write the expressions of pi as we have done. Pi is k is equal to 1 to n vi vk yik cos it is, we have already seen, it is vi square gii plus k is equal to 1 not equal to I in vi vk yik cos theta I minus theta k minus alpha ik. So, then if I do calculate del pi by del vk for k not equal to I, so then what I will get, this would be equal to vi yik cos theta I minus theta k minus alpha ik. This would be for I going from 2 to n, k varying from m1 to n, and k is not equal to I. Then the second term, that is this self term del pi by del vi, that would be from here to vi gii plus k is equal to 1 to n not equal to I, it would be vk y I k cos theta I minus theta k minus alpha I k. So, here what will happen? Here also we have I varies from 2 to n. Here also k varies from m plus 1 to n, but the rider is that k is equal to I. That is the only rider. So, these two terms together they do define J2 matrix. So, these two terms they do define J2 matrix, J2. So, now let us go to the matrix J3. Matrix J3 we have already seen it is del q by del theta. Now, vector q is q m plus 1, q m plus 2, q n transpose. So, this is an n minus m cross 1 vector, and vector theta is theta 2, theta 3, theta n transpose. This is n minus 1 cross 1 vector, and the definition of J3 is del q by del theta is del q m plus 1 by del theta 2 del q m plus 1 by del theta 3 dot 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 del q m plus 1 by del theta n, and it goes up to del theta del q n by del theta 2, then del q n del theta 3, and it goes up to dot 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 del q n by del theta n. So, it would be also a rectangular matrix. It is a rectangular matrix n minus m cross n minus 1. So, because it is a rectangular matrix, it will also have a self term and non self term. Self term should be del q I by del theta I. So, this is the self term, and non self terms would be in our own parlance it would be del q I by del theta k. This is k not equal to I, these are non self term. So, again we have to find out the analytical expression of this two elements, and if we can find that, so we can define this entire matrix. Now, to do that, let us write down the expression of q I. Q I is k is equal to 1 to n V I V k y I k sin theta I minus theta k minus alpha I k. Now, we have defined that y I k is equal to y I k magnitude and angle. So, this is g I k plus j b I k. This j is not the complex operator, and so then therefore, we know that g I k is equal to y I k cos alpha I k and b I k is equal to y I k sin alpha I k. So, this all this we have already looked into, we are merely writing it for our recollection. So, now here if we do take the ith term separately as we have done for the expression of p I, so then what I will get? So, if k is equal to I, so it becomes v I square y I. So, theta I and theta k cancels out. So, this is sine of minus alpha I k. Sine of minus alpha I k is nothing but minus sine alpha I because here k is equal to I. So, then it would be sine of minus alpha I. So, then it would be basically v I square y I into sine of minus alpha I, and we know that the sine of minus alpha I is nothing but minus sine alpha I. So, then if we do apply this, we do get minus v I squared b I plus k is equal to 1 to n not equal to I v I v k y I k sin theta I minus theta k minus alpha I. So, this is the expression of q I. So, now you have to find out first non-self terms del q I by del theta k. So, what it would be? Please kindly remember k is not equal to I here. So, the partial derivative of this would be 0. So, sine derivative cos, it has got a minus. So, it would be minus v I v k y I k cosine theta I minus theta k minus alpha I k. We are trying to differentiate this expression with respect to any particular specific k. So, this would be 0. So, this is the expression of delta q. Now, what would be the range of? So, for here I would be varying from m plus 1, m plus 2 to n, k would be varying from 2, 3, n, and k is not equal to I. It would be clear from here. So, k varies from 2, 3 to n and I varies from m plus 1 to n. Now, we have to find out the expression of del q I by del theta I. So, that would be is equal to, again it would be 0 and it would be k is equal to 1 to n not equal to I, only this term will come, but because theta I exists in all the expressions, in all these terms of this summation. So, then we will get all these terms of the summation and it will be very simple, v I v k y I k cosine theta I minus theta k minus alpha I k, and here the I would be varying from again m plus 1 to n, k would be varying from 2 to n, and the rider is k is equal to I. So, these two terms together define the matrix J3. The last one is remaining J4. So, let us do that. J4 is del q by del v. So, if I do del q m plus 1 by del v m plus 1 del q m plus 1 by dot 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 del v n, and it would go up to last one del q n by del v m plus 1, then del q n by del v m plus 2 dot 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 del q n by del v n. So, it would be a n minus m cross n minus m matrix. So, it is a square matrix, Last two were, this I must say that this is a rectangular matrix. This is a rectangular matrix. J2 is also a rectangular matrix. Okay. So, it is a square matrix. Now, because it is a square matrix, so then therefore, it would have diagonal terms as well as off diagonal terms. Diagonal terms would be obviously del q I by del v I, and that is the diagonal terms. And del q I by del v k, k is not equal to I, those would be off diagonal term. So, we again write down the expression of q I is minus v I square b I plus k is equal to 1 to n not equal to I v I v k y I k sin theta I minus theta k minus alpha y k. So, we first do the easier one del q I by del v k. So, this part derivative would be 0 and we will have only one term here, and that term would be v I. So, this v k will go y I k sin theta I minus theta k minus alpha I k, and here the I would vary from m plus 1, m plus 2 to n. K would also vary from m plus 1, m plus 2 to n, but the rider is k is not equal to I. The last one is del q I by del v I. So, here it is minus 2 v I b I plus, please note that in this expression of q I, in all the terms inside this summation symbol has got this quantity v I. So, then therefore, all these terms inside the summation symbol will come into picture. So, k is equal to 1 to n not equal to I, it would be v k y I k sin theta I minus theta k minus alpha y k. Please note that this V I is gone, and here what would be the variation of I and k? I again would be varying from m plus 1 to m plus 2 to n, k also would be varying from m plus 1 to m plus 2 to n, and the rider is k is equal to I. So, then therefore, these elements together define the matrix J 4. So, then we have found out all the expressions of all the elements of this Jacobian matrix. So, now what we will do? Now, please remember that at each and every iteration all these elements of this Jacobian matrix would be evaluated with the most updated values available for the quantities V and theta. V means all these bus voltages and theta means all these bus voltage angles. So, then therefore, once we get all these bus voltage, once we get the numerical values of all these elements of the Jacobian matrix, after that we can simply invert. Now, here one very interesting thing is that if we look at the expression of let us say J2, J3, J4, J2, J3, J4, apparently if we look at the expression of let us say J2, now the question is here, for example, there will be many such elements which will have this particular expression. Now, are all these expressions be non-zero? Now, we need to understand that when we would be actually evaluating this expression or let us say this expression, what we will do? We will simply substitute the latest voltage magnitude and the angles available for all these V I and all these theta I and theta k, and remember y I k and alpha I k are already known. So, then it may happen that all these elements del p I by del V k and del p I by del V I would be non-zero. So, then as a result this matrix J 2 would be an completely full matrix, but then one very important point to notice is that this value y I k would be 0 in the bus admittance matrix if bus I and k are not directly connected with each other. So, then therefore, if bus I and k are not directly connected with each other, so then therefore, many of these elements del p I by del V k would be 0. Only those elements would be non-zero where bus I and bus k are connected to each other, because in that case y I k would be non-zero and of course alpha I k will also be non-zero. What about this element del p I by del V I? This element would be always non-zero, because after all G I is nothing but the real part of the diagonal element corresponding to bus I. So, then therefore, this particular diagonal element will always exist. So, then therefore, G I will always exist. So, then therefore, this part would be always non-zero. But then again, depending upon the direct connection between bus I and bus k, here y I k may be 0, y I k may be non-zero. So, then therefore, even it may happen that we have to add all this sum total together, but then in effect probably only few terms will come. Similarly, if we look at the expressions of J 3 also, for this also only those terms would be non-zero for which bus I and bus k are directly connected, and here also basically those terms would be non-zero where bus I and bus k would be directly connected. Now, obviously there will be some buses here where at least bus I would be directly connected to bus k. So, then therefore, at least there would be one element here would be non-zero. So, then usually this self terms become always non-zero, but this non-self terms some of them would be non-zero, but the rest of them would be 0, because in any power system usually any particular bus is directly connected to mostly 4 to 5 other buses. We would be actually discussing this issue in much more detail in some later classes. Similar observation also holds good for this matrix J4. So, here also depending upon the case that where bus I and bus k are directly connected or not, this term would be either 0 or non-zero, but then this term would be always non-zero, and then again depending upon the fact that whether bus I and bus k are directly connected or not, this term, some of these terms would be non-zero and some of these terms would be 0. So, then therefore, what we can see is that in this matrix J2, J3 and J4, many of the elements would be 0. So, as a result, this matrix J2, J3 and J4 would be actually sparse in nature. Similar observation also holds good for this matrix J1. A matrix is called sparse when most of these elements are 0. So, now because this matrices J1, J2, J3, J4 are sparse in nature, so then therefore, this matrix J is also sparse in nature. So, this is one interesting observation. But now we have already done we have already covered all the mathematical necessities corresponding to Newton-Raphson polar coordinate. In the next lecture, we will be looking at the complete algorithm as well as one small example of NRLF in polar coordinate. Thank you.